Why does geometry matter? First of all, it's a major component in mathematical thinking. And secondly, it has played a vital role in human history. To give one example, using a bit of geometry known to every high school student, a person in 200 BC was able to calculate the circumference of the earth. His name was Eratosthenes, and he was a poet living in Alexandria, Egypt. He was also the chief librarian of the great Library of Alexandria, which was one of the 7 wonders of the ancient world. So, how did he manage to do it? Well, one day he was in a little town called Syene, which is now called Aswan. There were 3 significant facts about Syene. Fact number 1, it was due south of Alexandria. Fact number 2, it was exactly 500 miles from Alexandria. And fact 3, it was right on the Tropic of Cancer. The first fact meant that he had a meridian to do his measuring on. The meridian is a great circle of a sphere, or in this case of the earth, which means it is also the circumference of the earth. The second fact meant that he had a yardstick to do his measuring with. 500 miles was the exact length of an arc of the circumference of this circle. But how many degrees were in this arc? What part of 360 degrees was this distance? That's what he had to find out. The third fact was the most spectacular of all. The Tropic of Cancer is the line farthest north on the Earth, where the Earth meets the sun's rays coming straight down. Once a year, at the time of the summer solstice, June 21st, it would be the highest of all possible high noons on the Tropic of Cancer, and Syene was on that line. So, on June 21st, the summer solstice, Eratosthenes saw that the sun was so straight overhead that no shadow was cast. No pole, no wall, no building cast even the slightest shadow. More than that, the sun's rays lighted up a deep well. He realized if that well were to continue down to the center of the earth, that sunlight would go all the way down, and it would provide a radius of the earth. But Eratosthenes also was sure that in Alexandria, north of where he was at that very moment, poles and walls would be casting shadows, so that everything vertical up in Alexandria had to meet the rays of the sun at a certain angle. Everything vertical up there in Alexandria had to meet the sun's rays at a certain angle. And the curve of the earth made the difference between anything vertical here in Syene and anything vertical there in Alexandria. And that would be enough difference to measure. So next year, at the time of the summer solstice, he would measure the angle of the shadow in Alexandria. Now, how did he know that this would work? Because he remembered a theorem of geometry, that when parallel lines are crossed by a straight line, also called a transversal, alternate interior angles are formed, and alternate interior angles have the same measure. In other words, they are equal in the number of degrees that they have. Take a look at this diagram. The sun's rays are parallel. Say that angle O is the sun's angle at Alexandria, the angle that's hitting the pole. Then angle C is at the center of the earth. And if he knew how many degrees were in that 500-mile arc, he would know the circumference of the earth. So he set up a pole that was perfectly vertical up in Alexandria, and he waited for the next year's summer solstice, the time when the sun would be at its highest point overhead. When that day finally arrived, he measured the angle that the top of the pole made with the sun rays, creating the shadows. It would be the same angle that he was looking for in the center of the earth. It was 7.2 degrees. There are 360 degrees around the circle of the Earth. 7.2 is 1/50th of 360. So 50 times the 500-mile arc gave him 25,000 miles. That was the circumference of the Earth. Eratosthenes got it right within a few hundred miles. He did it in 200 BC, and he did it with geometry. We see geometry all around us, and the focus of this course is how can we foster geometric thinking among our students.